Hi students, Professor Gray here from home. That means you might hear a cat, a dog, or some kids in the background, but I'm sure you guys have the same. All right, I think I got this lecture video thing figured out. Cross your fingers. And we need to continue on with chapter 2 and then head on into chapter 3 this week. So what I want to do with you guys is just review slightly what we did before to remind ourselves where we were, and then finish up this chapter with electron configurations. So I have added a couple of periodic tables into this presentation to make it a little bit easier for you guys to understand what I'm talking about. So hopefully you can pull out your periodic table right now and follow along. So I want to go back to the slide where we were talking about lithium. So this slide right here, and look at what the periodic table tells us about lithium. Now it says that lithium has atomic number 3, and we said that that means that lithium has 3 protons. And if you have 3 protons, you're a lithium. So because protons are positively charged in our neutral lithium atom, we're also going to have 3 electrons because those are negatively charged. And 3 pluses and 3 minuses makes a neutral charge. So plus 3 and minus 3 equals 0. Now down at the bottom we have 6.94, and we talked about how that means that a lithium has an average mass of 7. And because for our purposes electrons don't weigh anything and protons weigh 3, that must mean that the rest of the mass comes from 4 neutrons. And when we took a look at this picture right here, we saw that indeed in the nucleus of our lithium, we've got 3 protons, 4 neutrons, and that's it for the nucleus. And then around the outside, we have 3 electrons. Now, our question was, where do the electrons go, into which orbitals? So that brought us to this part of the lecture, where we said there were a few different models that we typically see for our atoms, and one of them, this one right here, looked kind of planetary with the electrons going around in orbitals. This one too, and then we said this one right here shows us our electrons in a cloud around the nucleus. And then we talked about what our atomic orbitals look like. So we said that an orbital is a region of space where our electrons are going to be found, and the electrons of interest have highest probability of being in this orbital or that orbital, depending on which electron they are. And we had 4 basic shapes for our orbitals. We had S, which is a spherically shaped orbital. And we had the p orbitals, and those come in 3s. So we'd have px, py, and pz. And then we had the d orbitals, and when you open those up, you get 5 at a time. And remember, each orbital can hold 2 electrons. So if we've got 5 d orbitals, those 5 d orbitals altogether can hold 10 electrons. And then we had even higher in energy, our f orbitals, and those come in 7s. And each one of those f orbitals can hold 2 electrons, so the f orbitals altogether can hold 14 electrons. Now, putting all of those together in a picture format, it would look like that. And if we took a look at our energy levels, it would look like that. So we can see that our first s orbital, the 1s down here, is the lowest energy. And in lecture, when we were in class together, we said that electrons are like people. They tend to do what's easiest first. So our first two electrons are going to head on into the 1s orbital. Now, the 1s orbital is closest to the nucleus. You guys can see that right here. That's going to be a spherically shaped orbital around the nucleus, and all that's there is that 1s orbital. Now, if we fill that 1s orbital with 2 electrons, the third electron has to go somewhere else. So we have to open up more space. So we open up what's called a shell. And in the second shell that opens up, or the second space for our electrons, we have 2 subshells. We have the 2s and we have the 2p's. And remember that the p's come in threes. So if we fill the 2s with 2 electrons, and then we have more electrons to put somewhere, we're going to get 3 options right away. The 2py, the 2pz, and the 2px, again, that we have right there on that picture. So the p's and the s's are subshells in the second shell. Now all that's in the first shell again is just that 1s orbital. So the first shell only has 1 subshell, which is the shell, which only has 1 orbital, which is the entire shell. Okay, if that makes any sense. All right, so looking at the first 2 elements, so we have hydrogen and helium here. Now, remember, hydrogen is our first element right there. It has atomic number 1. Now, that means that it has 1 proton and 1 electron in the neutral atom. And where is that 1 electron going to go? Well, it's going to go in the easiest place, and that is in the 1s orbital. And you guys can see that right there. We've got that 1 lonely little electron right there. And we can indicate this to our reader in a couple of ways. So the first one is with an orbital box diagram. So let me just write box right there. So what we do is we draw a box, and that indicates an orbital. So we can label this box right here as our 1s orbital. And for the hydrogen, we just put 1 electron in there. And the electron is symbolized by an arrow with 1 arm. And convention states that if there's just 1 there, we draw that up. And the other way to indicate where that electron is going is the electron configuration, which is on the right here. So what we do is we say that we've got 1 electron, and that's that 1 right there. And that 1 electron is in the 1s orbital, which we put right there. So the electron configuration for hydrogen is 1s1. Now for helium, which is over here, that is atomic number 2. So we've got 2 protons and 2 electrons there. So how we draw the orbital box diagram for helium is right here. And we draw that box and we label it as the 1s orbital, and we put those 2 electrons in that 1s orbital. The first electron is pointed up, just like it was in hydrogen, and then the second electron, we point that down. And if you guys take a look at the bottom of the slide, you can see that that's the Pauli exclusion principle right there. And what Pauli said is that orbitals can hold up to 2 electrons, but the electrons have to be of opposite spin. And in chemistry, the way we indicate that is 1 of our arrows up and 1 of our arrows down. In physics, you will see it as +1/2 and -1/2. Now the electron configuration for helium, again, just a different way of explaining where the electrons are going from the orbital box diagram, is written this way right here. So what we say is that there are 2 electrons in this 1s orbital, and the way we say that is that the electron configuration for helium is 1s2. Okay, so let me move on to this slide right here. And we can see that the first element that we have on the list on this slide is lithium. And lithium has 3 electrons. And how did we know that if we weren't listening in the beginning of the lecture? Is by looking at the periodic table that you guys should have next to you right now and seeing that lithium is right here, and it's an atomic number of 3, which means that it has how many protons? 3, that's right. And that means that it has 3 electrons. So the first 2 electrons in lithium are going to go into the 1s orbital because that's where the first 2 electrons always go. And you guys can see the orbital box diagram right here is putting the first 2 in that 1s orbital. Now remember, in the first shell, all there is that 1s orbital. There's no p's, there's no d's, there's no f's. So we have to also deal with that 3rd electron. And the 3rd electron in lithium has to go somewhere else. So the next place that it can go is into the 2s. And if we look back over here at this slide, we can see why, and that's because the 2s orbital is the next lowest in energy. So that's the next easy place for it to go. So for lithium, we'd have 2 electrons there, and we'd have the 3rd electron putting itself right there if we're talking about energy levels. And if we are going to indicate this with our orbital box diagram, we would draw another box for the 2s orbital, and we'd put that 3rd electron right there. Now, if we're going to explain where the electrons are going in terms of electron configuration, which again, remember, is the same exact thing as the orbital box diagram, it's just a different way to write it. We would say that the first 2 electrons go in the 1s orbital, and that 3rd electron goes in the 2s orbital. And the way we say that is that the electron configuration for lithium is 1s2, 2s1. Now, the next atom is beryllium. So beryllium is atomic number 4. So we are right here. So beryllium has 4 protons and 4 electrons. The first 2 electrons are going to go in the 1s orbital, like they always do, and the next 2 electrons are going to go in the 2s orbital. So how we say the electron configuration for beryllium is 1s2, 2s2. Remember that the superscripts up here, the 2 and the 2, those are telling us how many electrons. And the 1s right here and the 2s right here, oops, let me get that right there, that 2s, those are telling us which orbitals they're going into. All right, the next element is B. What's B, you guys? B is boron. Boron is atomic number 5. We're right there. So we've got 5 protons and 5 electrons. So we put the first 2 in the 1s orbital and the second 2 in the 2s orbital, and then we've got a 5th electron that needs to go somewhere. And the next place that the electrons can go are into the 2p's. Now the 2s and the 3 2p's, they are all in the second shell, but the 2s and the 3 2p's, 2px, 2py, and 2pz are all in the same shell. And you guys can see on the energy diagram that the 2p's are a little bit higher in energy than the 2s's. So that's where electrons are going to go next after we fill the 2s. Now we could also write these 3 right here as 2px, 2py, and 2pz. but the diagram chose to just go easy on us and put that there's 3 p's there. Now you guys can see that those all sit at the same energy level. So we can think of those as triplets right there. Now, our first electron to go in the 2 p's, we write it in the first box right there, and we write it up because convention states that the first one there will be written up. So right here where we have 2p at the bottom of the 3 2p boxes, we could also write 2px, 2py, and 2pz, but the diagram wrote it in shorthand and just said, here you've got 3 2p orbitals. So our third one goes there. Now with carbon, we've got 6 protons and 6 electrons. Excuse me. So our first 2 electrons go into our 1s orbital as always. The second 2 go into the 2s orbital as always. And then we have 2 electrons to distribute to the 3 2p orbitals. Now, it would seem logical for us to put the second electron that's going into the 2p's right there and pair it with the first electron right there. But Hund's rule says that electrons pair, which we did right there, we paired them. Electrons pair only after each orbital of equal energy is occupied by a single electron. Now what we're talking about there is that those 3 2p orbitals right there all sit at the same energy level, and we can see that right there. And like I said, they're triplets. So if you have triplets, you have to give each one of them a hamburger before you give any one of them 2 hamburgers. So we're going to go ahead and erase what we did right there. And we can see that we're back at giving our 2px and our 2py a single electron before we pair 2 electrons in the 2px. So the way that we say the electron configuration for carbon is 1s2, 2s2, 2p2, because there's 2 electrons in the 1s, there's 2 electrons in the 2s, and there's 2 electrons in the 2p orbitals. We could also write that as 1s2, 2s2, 2px, and the 2px has 1 electron in it, and the 2py has 1 electron in it. And because the 2pz doesn't have any electrons in it, we wouldn't write it. And that would also be correct, but this one is easier to write. So we just say 2p2 with the understanding that those 2 electrons are going to be distributed into the 2px and the 2py before we would put 2 of them in the 2px. Okay, so let's do a few of these. So I split up this problem page into 2 different slides, but it has all the same elements as your slide does, the original that you guys downloaded. So the problem says determine the electron configurations for the following atoms. So we have nitrogen. Now nitrogen is right here. We've got 7 electrons. Now, the first 2 electrons, we're going to put those in which orbital? The 1s, right, because the first 2 electrons always go in the 1s. So we have 1s2, and then we have 2s2, because after you fill up the 1s, you go on to the 2s. And then we have the 2p's that are going to start to fill. So just to remind ourselves how many electrons we're working with, again, nitrogen is atomic number 7, which means it has 7 protons, and it has 7 electrons. So I'll just put the E minus for electrons and then apostrophe S for 7 electrons. So we've used 2 of them. In the 1s, 2 of them in the 2s, and that means we have 3 left, so we will put those 3 in the 2p's. Okay, so again, the other way that you guys could write that if you wanted to indicate that each of your p orbitals got one of those electrons, so we would follow Hund's rule, is this way, but most of the time we'll just write it that way and assume that our reader understands what we mean. Okay, so then the electron configuration for nitrogen is 1s2, 2s2, 2p3. All right, moving on to oxygen. Oxygen is atomic number 8, and that means that we've got 8 protons and we've got 8 electrons. So the first 2 are going to go in the 1s orbital. So we have 1s2, 2s2, 2p, and then this time it'll be 2p4 because we need to distribute 8 electrons, and 2 plus 2 plus 4 is 8. Okay, so we've got 1s2, 2s2, 2p4. That means that if you wrote it out the long way, we'd have 1s2, 2s2, 2px, and the px would get 2 electrons, and we'd still have the py with 1 electron and the 2pz with 1 electron. So the orbital box diagram, the way that we would write that would be, we'd have our 1s orbital, and it'd have 2 electrons in it. And then we'd have our 2s orbital, and it'd have 2 electrons in it. And then we would draw 3 2p orbitals, and we'd stick them all together to indicate that they're at the same energy level and they come open together. And we could just put a 2p down there, or again, you could put 2px, 2py, and 2pz, and we'd say that we're going to give each of these 1 to follow Hund's rule, and then the very last one, the 8th one, goes right there in that first one. Alrighty, so that would be the orbital box diagram for oxygen. So we've got 2, 4, 6, 8 electrons there. Okay, moving on to neon. So with neon, we are at atomic number 10. So that means we've got 10 protons and 10 electrons. So the first 2 electrons are going to go where they always do. We're going to say 1s2. And then the next 2 electrons are going to go into the 2s. So we have 2s2. And we've used up 4 of our 10 electrons, and that means we need to place 6 others, and the next place that electrons can go are into our 3 2p orbitals. So 2px can have 2, 2py can have 2, and 2pz can have 2, and that means that we can just shorthand that and put 2p6. So neon has an electron configuration of 1s2, 2s2, 2p6. On to sodium. Sodium is down here. That is atomic number 11. So we have 11 protons and 11 electrons. So sodium, 11 electrons. So we have 1s2, 2s2, 2p6, and now we have an 11th electron that we need to put somewhere, and the question is, what on earth comes next? Well, there's a few different ways that we can look at this. The first one is we can take a look at the energy diagram, and we can see, okay, after I fill up my 2p's, the next one is the 3s. So if we go to this picture right here and we see that we fill up all of those orbitals, what would happen is next we're going to open up the third shell. So boom, our atom is getting bigger. The electron cloud is getting bigger. So we have 3s that opens up. And then we can see that after we fill the 3s with 2 electrons, we'll go to the 3p's. So hopefully this is making sense at this point. And if we want to look at it an even different way, we can take a look at this slide right here. And we'll see that sodium is right here, atomic number 11. And this chart will indicate to you that the electron configuration for sodium should end at 3s right here, because that's where it is. All right, so since the next orbital that we're going to start filling is 3s, we would say 3s1. So sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. Now if we were to write the orbital box diagram for that, how we would write that is we would say 1s, and this one is 2s, and then we'd have the 2p's, and those are all of the same energy level. So again, we're going to smush those together like that, and then we have 3s. And we'd say we've got 2 electrons in the 1s, we've got 2 electrons in the 2s, we've got 6 electrons in the 2p's, and then we put that one lonely electron in the 3s. And we've got 2, 4, 6, 8, 10, 11, and that matches right there. All right, so this video, I'm going to stop at this point and see if I did it correctly and try to get it up on YouTube for you guys. So again, cross your fingers and hopefully we'll get done with chapter 2 in the next video.